So hi students, I am your Vishal sir, and today I am going to continue the RE-NEET series. So today's chapter is work, energy and power. This is one of the most important chapters. So let's start without wasting time. Okay, so work, energy and power. Now, how we have defined work? That work is basically dot product of force and displacement. F is force, S is displacement, and dot product A dot B is AB cos theta. So F dot S will be Fs cos theta. So work is force multiplied by displacement multiplied by cos of theta, where theta is the angle between force and displacement. Theta is the angle between force vector and displacement vector. Correct. Now, see, like if we see the SI unit of work, what is the SI unit of work? So SI unit of work we can write. What is the SI unit for force? Newton. For displacement, meter. Cos theta. So cos theta is the ratio. So no unit. So Newton meter. So the SI unit of work is Newton meter, or this is also called joule. Correct. Its CGS unit of work is erg. And we should know the relation that 1 joule, 1 joule equals to 10 to the power 7 erg. So this relation also we should remember. Joule is the SI unit, erg is the CGS unit, and 1 joule equals to 10 to the power 7 erg. Clear? Now, since work is a dot, you can see it is a dot product of force and displacement. Definitely, what we can write that work is a scalar quantity. Work is a scalar quantity. Okay. Okay. So, for example, this force they have given 2 I cap plus 3 j cap, and there was a particle whose initial position was, suppose, I cap plus 2 j cap, and whose final position is 4 I cap minus j cap. So this is the initial position of the particle, this is the final position of the particle. If they ask what is the work, so work is F dot S. F dot S. Now, force is 2 I cap plus 3 j cap dot displacement we have to see. So displacement, what we can write? Displacement is what? Final position. R final minus R initial. So final position vector is 4 I cap minus j cap minus initial position, that is I cap plus 2 j cap. So 4 I cap minus I cap will be 3 I cap minus j cap minus 2 j cap will be minus 3 j cap. So this is our displacement. So in place of displacement we can write this is force dot displacement. Displacement will be 3 I cap minus 3 j cap. Now we know dot product how to solve. This I and I coefficient will be multiplied. So 2 3s are 6. Similarly, j and j components will be multiplied. So 3 into minus 3, that is minus 9. So 6 minus 9, we are getting minus 3. So minus 3 joule is the answer. We know it is a scalar quantity, so minus has importance. So minus 3, minus is not telling about the direction because it is a scalar quantity. Minus 3, it's telling the magnitude, minus 3. Now see, so normally whenever you are applying this formula, that work equals to F dot S. Always remember that you apply this formula when this force is constant. When this force is constant. Now, first of all, many students struggle. Like I have seen many students, they will struggle to tell that whether force is constant or variable. Let me give some example. Like if they give force equals to 2 Newton, so we know this is constant. There is a constant force of 2 Newton. They give force equals to, suppose 2 I cap plus 3 j cap. Now here comes the problem. So most of the students think that we have I and j variable, so it is a variable force. No, I and j just tell about direction. This I and j just tell about the direction. What is the meaning of this? Suppose there is a block. 2 Newton force acts in east direction and 3 Newton force acts in north direction. So the total force we have written 2 I cap plus 3 j cap. So you can find the value, now it is constant only. You remember vector? If we want to find the magnitude of this force, what you will do? Under root I coefficient square plus j coefficient square. So 2 square plus 3 square. So this will be under root 13. So under root 13 means something between like under root 9 is 3, under root 16 is 4. So something between 3 and 4. Suppose I am taking for example approx 3.5. So see, we are getting the constant value. So this force, whenever you see like this kind, so this is a constant force, not a variable. So what are variable forces? So whenever you see force, it like in the form of like see 2t. This force is a function of time. You change the time, force will change. Time equals to 0, force equals to 0. Time equals to 1, force equals to 2 Newton. Suppose you see that force is like 2x I cap plus y square j cap. See, this is variable force. It depends upon x and y coordinate. If x value is 0, y value is 0, force is 0. If x and y value is 1, so 2 plus 2 I cap plus j cap. So see, you change x, the value of force will also change. So this is a variable force. Correct? So this is the x component of the force. This is the y component of the force. Now how to find the work for variable force? How to find if the force is variable force? I am writing here. If the force is variable force, then work is written as integration of F dot ds. F dot ds displacement. Now, suppose force is expressed as some x component of force I cap plus some y component of force j cap plus some z component of force k cap. Then how we write work? We write work equals to integration of this whole term dot ds. So fx dx we can write fx dx plus integration of fy dy plus integration of fz dz. Okay, from x initial to x final, from y initial to y final, from z initial to z final. So this formula, you remember, this is very important. Whenever the force is variable, always use this formula. Wherever the force is variable, always use this formula for work. Integration of fx dx plus integration of fy dy plus integration of fz dz. I will take one example so it is more clear. For example, by F, force is given as x I plus 2y or y square j cap. Correct? So you can see this is a variable force. X and y are there. Now there is a particle whose initial coordinate was suppose 1 comma 2, and it due to the action of this force, so there is a particle, force is applied, suppose this force is applied, so its coordinate changes, suppose it is like final position is here. Just example I am taking. So the final coordinate of the particle, it becomes suppose 2 comma 3. Now they will ask what is the work done in this entire process. What will write work done will be integration of fx, x component of force, x, fx dx plus y component of force, y square. This is the x component of the force. This is the y component of the force. So y square dy. We don't have z components here. Now, what was the initial x coordinate? 1. What is the final x coordinate of the particle? 2. Similarly, what was the initial y coordinate? 2. What was the final y coordinate of the particle? 3. Now you have to solve this. Integration of x square by 2. Integration of y square, y cube by 3. And then you have to set the limits. 1 from 1 to 2, and here from 2 to 3. Now rest is mathematics. I am not here to do the calculation because in short duration we have to complete the chapter. So you can do upper limit minus lower limit and get the answer. So this is how we are solving this work done for a variable force. Now next is, see, if suppose force versus displacement graph is given, and if there is any curve, so what will be the area under the graph? So general formula always you remember. I told you now in basic mathematics. Area under the graph is if y versus x graph is there. So we write area equals to integration of y dx. If in place of y we have force and in place of x we have s. So what we will write area under the graph? So area under the graph will be f ds. And what is f ds? Work. Means what we can say that area under force versus displacement graph is nothing but work. So this point is also very important. Okay, let's take one question. For example, a graph has been given like this. So they have given this value 4, this value 2, this value 6, this value 8. Okay. So they are asking what is the work done? Work done in this process. What is the work done in this process? So work done is nothing but area under the graph. So area under the graph, you see. So just we'll draw like this. This also you. Now one thing is very important. The area which is above the x-axis, we consider that positive, and the area which is below the x-axis, we consider that negative. Means this area will be considered positive, however this area will be considered negative. So this area will be area of triangle. So half, base is 2, height is 4, and this area will be positive, and this area of a rectangle. So this is 2, this is 6, length will be 4. So length will be 4, and this breadth is 8. So 4 into 8, and since this is below the x-axis, we will write negative. So this will be the answer. Work done. Correct? Work done. So these kind of questions can be asked in the exam. You have to be careful. Correct? Okay. Next we have conservative force. Conservative force versus non-conservative force. Correct. So what are conservative force? Conservative force are those force work done by whom does not depend upon path. Means whatever path they take, work done will be same if the initial point and the final point is same. Hope you didn't understand. See, for example, I will give. Like suppose you want to go from your home to the airport. You booked one cab and you told the driver that, Bhaiya, I want to go from home to the airport. Whatever path you take, whether you take the long route or you take the shortest route, I will give you the same fare, that is 500 rupees. Right? Whether you take the long route or you take the short route, I will give you the same fare, that is 500. So here you can say this fare is conservative in nature. Means this does not depend upon path. Your fare does not depend upon path. Similarly, conservative force are those force work done by whom? Work done by these force does not depend upon path. It depends upon initial position and final position. Here, non-conservative, just opposite, means it depends. So just opposite, I am writing, I will not write the entire sentence. So just opposite. Second point, I will explain it further more. Second point, work done in round trip. Work done in round trip. In case of conservative force is 0. Here it is not 0. Here it is not 0. I will explain these 2 points. Some examples you write down. Gravitational force. We have gravitational force. We have electrostatic force. Electrostatic force. We have spring force, etc. So these are conservative forces. And in non-conservative forces, you write down friction force. So friction force, friction, air drag means air resistance. All these are means friction kind of things. All these are non-conservative force. So let's understand point number 1 and point number 2. What I told, see, for example, like there is a ball. You are releasing from point A to point B. This ball is at a height h from the ground. This is the ground and you are releasing the ball. So the initial position of the ball is this and the final position of the ball is this. Now if someone asks what is the work done by gravity? What is the work done by gravity? Via path AB means we are following the path AB. In the example I have given that gravity is a conservative force. And what I have told about conservative force, that work done by it does not depend upon path. Whatever path you follow, work done will be same. So what is the work done by gravity? So gravity is applying force mg downward and displacement is also h downward in the same direction. So we can write force into displacement mgh. Theta will be 0 obviously because both are in the same direction. So cos 0, 1. So mgh. Now, suppose we follow some different path like from A to C and then again C to B. Okay. So what we are doing? First we are moving the ball from A to C and then from C to B. We are changing the path, but the initial and final position remains the same. Now let's find what is the work done by gravity. Work done by the gravity by path A to C to B. A, C, B. So I can break it into two parts. Work done during part AC plus work done during part CB. Correct. Now work done during part AC, C. Force of gravity will always act downward in this direction, that is mg. Correct. And during A to C, displacement is in this direction from A to C. Suppose this displacement A to C, this AC distance, I am telling this is L. Correct. What is the angle between the force and displacement? So this is the force and this is the displacement. So this is the angle. This is the angle, suppose theta. So work done during path A to C, what we can write? Force, that is mg, displacement, that is L, and cos theta. Correct? Plus work done during path C to B. Now C to B again, see, this is the ball and gravitational force is mg and displacement of the object is from C to B, means in this direction. Correct? Now you can see force and displacement are perpendicular to each other. So what will the work done? Force multiplied by displacement multiplied by angle between them. Angle between them is 90 degrees. So cos of 90 degrees. Cos 90 degree 0. So if force and displacement are at 90 degree, there will be no work. You can see force and displacement are at 90 degree, there will be no work. So work will be 0. Now see, in this triangle ACB, what is cos theta? Cos theta general formula is base by hypotenuse. So this is the base h by hypotenuse length, that is L. So what we can write? Cross multiply L cos theta equals to h. From here, mg L cos theta is h. So we are getting mgh. So see, whether you followed path A to B, the work done by the gravity is mgh. Whether you followed the path A to C, C to B, the work done is mgh. Means work done does not depend upon path. It just depends upon initial position and final position. So these kind of force, gravity, these are conservative force. Correct? So we have proved how this gravity is a conservative force and what is the meaning of this initial path, final path, different path and all. Correct? Okay. Second point. What was my second point? That work done in the round trip by conservative force, that if we have a conservative force, so work done in the round trip is always zero. For example, this is the ground, there is a block, there is a ball, and you projected upward. It goes to a height h. So round trip means, see, first it will go from A to B. Then what will happen? The ball will come down. So this is a round trip, means from going from A to B and then coming from B to A. So work done is the round trip. Work done, round trip. Let's check. So this is work done in going from A to B plus work done in going from B to A. So work done by the gravity in going from A to B. So gravity always apply force in the downward direction, mg. But displacement, when it is going up, is in the upward direction, just opposite direction. So what is the work done? Force multiplied by displacement multiplied by cos of angle between them. So force is mg, displacement is h, angle is 180 degree. So cos of 180 degree minus 1. So work done will be mg, displacement is h, cos of 180 degree, that is minus 1. Now when it comes down, when the ball comes down, what is the work done by gravity? So again, gravity is applying force in the downward direction, that is mg, and displacement is in the downward direction, only same direction. So we can write plus mgh. So minus mgh plus mgh, it becomes 0. See, work done in the round trip by conservative force like gravitational force is coming out to be 0. This is the meaning of this. Correct? So these things you should be able to understand. Let's form one question. They can give like this. Okay. So this is A, this is B, this is C. So they are saying that there is a ball and any conservative force, not gravity, any conservative force acts on the ball. And work done in going from A to C is suppose minus 15 joule. Correct? And work done by the conservative force in going from A to B, they have given minus 5 joule. And they are asking what will the work done in going from B to C. They have asked. See again, this condition they have given, which kind of force is existing? Conservative force is existing. Correct? What we can write? Work done in going from A to C. A is the initial position, C is the final position. Whether you follow this path or you follow A to B and B to C. Whether you follow this path or you follow this path, work done will be same because it is conservative force. Means work done by a path A to C is equals to work done by a path A to B plus work done by a path B to C. So A to C it's given minus 15, A to B it's given minus 5 plus work done by a path B to C. So B to C, how much it will come? It will come minus 10, minus 10, minus 5, minus 15. So from here you can write work done by a path B to C is minus 10 joule. Correct? So this example is important. Correct? Next. Next we have to learn about kinetic energy. So any object which is in motion, which is having some speed v, it possesses some kinetic energy, and that is equal to half mass of the object square of the speed, half mv square. Acha, kinetic energy and all kind of energy, first of all, it is a scalar quantity, it is not a vector quantity. Okay. So kinetic energy formula is half mv square. Kinetic energy, we have one more formula, P square by 2m, and this is very important, P square by 2m. We can write in this passage also, where P is the momentum, where P is nothing but momentum. What is momentum? Mass into velocity. You can check also, like if we solve P square by 2m, what we are getting? So P is momentum, so momentum square, so m square v square divided by 2m. So this square and this m will be cancelled. So we are getting half mv square, that is kinetic energy. So kinetic energy equals to P square by 2m. So this result is very important. Okay. Now if you cross multiply, what you will get? That P square equals to 2m kinetic energy, or momentum equals to under 2m kinetic energy. Very important formula. It is widely used throughout our 11th and 12th course. That momentum equals to under twice m kinetic energy. They can give some questions also like this. For example, that kinetic energy is increased by 300%. So final momentum will become x times initial momentum. What is x? See, like if I write initial momentum equals to under root 2m kinetic energy, under root 2m kinetic energy. Initial kinetic energy is how much? Kinetic energy I am writing. So final kinetic energy, what is happening with final kinetic energy? Final kinetic energy is increased by 300%. So what is 100% of, suppose x? 100% of x is x. 200% 2x. 300% 3x. Means kinetic energy is increased by 3 times. So if Ke was initial kinetic energy, final kinetic energy will be initial kinetic energy, that is Ke, plus how much it increased? It increased 3 times, 300%. So 3 times kinetic energy, that is 3 Ke. So final kinetic energy becomes 4 Ke. So final momentum you can write under 2m final kinetic energy, that is 4 times initial kinetic energy. So you can write like this, under root 4 into 2m initial kinetic energy. So under root 4 will be 2 and under root 2m Ke is what? Initial momentum. So means we can write this is equals to 2 times initial momentum. Under root 4 is 2 and under root 2m kinetic energy, under root 2m kinetic energy is P. So 2p, 2p, this is our answer. So final momentum, this x value we are getting 2. This x value we are getting 2. So these kind of small questions can be asked in the exam. Correct? Next, potential energy. Potential energy. See, potential energy, first we consider one reference level. Like suppose this is the ground and this is our reference line. Reference line. So here what we take, that potential energy, suppose we take 0. And there is a mass m. If it goes to a height h above the ground, if the ball is here, someone asks what is the potential energy right now. So potential energy formula is mgh. Correct? We all have studied if an object is at a height from the ground, its potential energy will be mgh. Achha, we are considering this h value is far lesser than this radius of the earth. Similarly, if this object goes down, suppose x distance down it goes, and someone asks what is the potential energy here. So mg height or depth is x, but here we will write minus. If it goes below this reference line, so this minus mgh. Right? So this is the concept of potential energy. Always remember that potential energy depends upon reference, where you have taken the reference. But change in potential energy is independent of whatever reference you will take. It will be the same, independent of reference. So sometimes in statement-based questions they ask this statement that potential energy depends upon reference, but change in potential energy is independent of the reference line. Correct? Now see, when we are discussing potential energy, we should also learn what is the potential energy of a compressed or stretched spring. So again, I am not going for the derivation. Just you remember that suppose this was the natural length of the spring and we compressed it. Suppose there was one block attached to it, we applied some force and we compressed this. This is called the natural length of the spring. Right now we have not disturbed the spring. So this is the natural length of the spring. Now if we compress or if we elongate, whatever, like for example, let me draw the diagram. Suppose I compress the spring and it becomes like this. So how much distance we have compressed? So you can see this much distance we have compressed. This I am calling x. Okay. So if you have compressed the spring x, the potential energy stored in the spring will be kx square by 2. Where x is how much you compressed, or sometimes you can stretch also. Same formula will be there. Like if someone stretches by x amount, the potential energy stored in the spring will be kx square by 2. What is k? Spring constant or stiffness constant. Stiffness constant or spring constant. So this you should remember. Correct. Also, sometimes little bit like they twist the question. What they give now, that they will say that initially, like suppose this was the normal length of the spring. Initially, the spring is compressed. The spring is compressed. We have compressed the spring. Okay. By how much distance? By xi. Correct. And draw like this. A little bit. Okay. So we have, this is the x initial compression. This much we have compressed. At t equals to 0, the spring was compressed. Means initially this is the condition. The spring was already compressed. Now, we furthermore, again we compress the spring. Again we compress the spring. And this is the final structure. So we have to check from the natural position. Remember, like mark my words, from the natural position, how much distance it has been compressed. Means from this point, how much it has been compressed. So we can see from this point, it is compressed this much. So this is x final. So potential energy stored in the spring formula is K by 2 x final square minus x initial square. Correct? Where x final is final compression and x initial is xi initial compression or elongation, whatever it's given in the question. And just always remember this x final and x initial both we take from natural length of the spring. And from natural length, how much it was initially compressed. Similarly, from natural length, how much it was finally compressed. For example, I will take one question that they have given. The initial compression of the spring is suppose 2 units or 2 centimeter. Correct? Now they have written xi. What is xi? Initial compression of the spring. Initially, how much it was compressed. Now it's written spring is further compressed by 3 centimeter. Find potential energy of the spring. Now what people do? They will write K by 2 x final is 3 square minus x initial, that is 2 square. And here they get trapped. This is the wrong answer. Why? What they are saying, see, initially the spring was compressed by 2 centimeter and further it was compressed 3 centimeter. Means what was the final compression? from the natural length. 3 plus 2, 5. See, suppose this is the natural length. So what they are saying, initially they have compressed by 2 centimeter, and finally they have compressed. They are more compressing further. They are compressing by 3 centimeter. This again they are compressing this. This value is 3 centimeter. Correct. So x initial is 2. This is fine. But x final. What I told, we compare from the natural length. Natural length was there. Here. So from here it is compressed to here. So what is the total compression? 2 plus 3, 5. So the real answer will be k by 2 x final. That is 5 square minus x initial. That is 2 square. This will be our answer. So be careful while solving this. Correct? Now, okay. See, work energy theorem, which is the backbone of this chapter. Work energy theorem. What it says? It says that work done by all the forces is equals to change in kinetic energy of the system. Change in kinetic energy means final kinetic energy minus initial kinetic energy. This is work energy theorem. I will explain what it is saying through one example. For example, there is a block. You are applying force of 5 Newton. This block is of mass 1 kg, suppose 1 kg. This like surface is rough, and the coefficient of friction is mu value is 0.5. Suppose you have applied let's say 75 Newton, okay? And this, what I'm saying, this surface is rough, coefficient of friction is 0.5. You have applied 75 Newton force. This is the 1 kg mass. So this mass gets displaced from here to here. And this displacement also they have given. That displacement, they have given 100 meter. Means if you see the displacement of the center, this is 100 meter. And it is not stopped. It has not stopped. I am not saying that it has stopped. Means what is the question? Again, you listen carefully. There was a block of mass 1 kg. It was kept on a rough surface. You applied 75 Newton force. When it got displaced by 100 meter, when initially it was at rest. Initially this was at rest. When this got displaced by 100 meter, what is the speed of this block? This is the question. What is the speed of, right now the block is moving with what speed? We will like apply work energy theorem. So work done by all the forces. First you have to see what forces are acting on the block. So one force is definitely, one of the forces is definitely mg, and mg will act downward direction. This will be mg, mass is 1, g is 10, so 10 Newton. One force will be normal. One force is this external force, 75 Newton. And since the block is moving, friction will oppose, so friction will act in the opposite direction. What is the value of friction? Friction will be its maximum, and this will be mu into n. Here, what is n? Because the block is not going up and down, so normally we can write normal is 10. Here, normal value is 10, and mu value is given 0.5 means half. So friction maximum will be mu into n means half multiplied by 10. That is 5 Newton. So friction is nothing but 5 Newton. This is friction. Now you have to calculate work done by all the force. This total 4 force, one mg, one normal, one external force 75 Newton, and one is this friction. Now you know that this normal reaction and this mg will not do any work. Why? Because these forces are perpendicular to displacement. See the displacement now? Displacement is in this direction. This is the displacement. If I draw what is the displacement vector, so this is our displacement vector. This is our displacement vector from here to here. Correct? So this force normal is perpendicular to this displacement, and this mg is also perpendicular to this displacement. There will be no work. Angle 90 degree. So there will be no work due to this normal and due to this weight. Now work done by this 75 Newton. So work done, because it's given work done by all the forces. So work done by this 75 Newton will be force, that is 75, multiplied by displacement. Displacement in the same direction, that is 100 meter. Now what is the work done by friction? Friction is 5 Newton. And displacement is 100. But friction and displacement are in just opposite direction. So force multiplied by displacement multiplied by cos of 180 degree, that is minus 1. Means force, that is friction force, is 5 multiplied by displacement, that is 100, multiplied by cos of angle between them. So friction is here, displacement is here, angle is 180 degree. Cos of 180 degree means minus 1. So this is the work done by friction. So we have calculated work done by all the forces. See, work done by this is 0, work done by this is 0, work done by this is 35 into 100, and work done by friction is minus 5 into 100. So work done by all the forces equals to change in kinetic energy. So final kinetic energy, that is half, mass is 1, speed, square of the speed here, minus initial kinetic energy. Initially the object was at rest, so 0. So you can solve this, everything is given, you have to find the speed. You can solve it later on. So this way we are going to solve questions based on work energy theorem. Correct? Most of the times they ask speed, so you can like use work energy theorem. Okay. Okay. Next, see, one thing you should remember, that work done by, and this is very important, work done by conservative force is equal to negative of work done by external force is equals to negative of change in potential energy. This point is very, very important. Correct? This point is very, very important. Okay. So see, for example I will also take, like suppose there was a ball and you projected it upwards to a height h. Conservative force, gravity, work done by gravity. So gravity is acting downward, displacement is upward. So we can write minus mgh. Achha, what is the work done by external agent? External agent means we only projected the ball, no? So we apply force in the upward direction. Displacement also in the upward direction. Achha, in order to throw any object, suppose object weight is 100 Newton and it is kept on a table. So in order to lift it, how much force you have to apply? 100 Newton, because its weight is 100 Newton. So you have to apply 100 Newton. Correct? So in order to lift it, you have to apply force how much? Mg, and you are projecting it upward. Means you are applying force in the upward direction, displacement is also in the upward direction. So work done will be force, that is mg, weight of the body, multiplied by displacement, that is h. And this will be positive. So you can see work done by conservative force and work done by external force, they are negative of each other. This is minus mgh, this is mgh. So work done by conservative force equals to minus of work done by external. Achha, what is the change in potential energy here? Change in potential energy means final potential energy minus initial potential energy. Final potential energy here, when the object reach this position, so here potential energy is mgh and here initial potential energy was 0. So final potential energy, that is mgh, minus initial potential energy, that is 0. So change in potential energy is mgh. You can see work done by conservative force minus mgh and change in potential energy plus mgh. Means they are negative of each other. So work done by conservative force equals to negative times change in potential energy. So we can write this also, that work done by external agent equals to change in potential energy. See, work done by external agent mgh, change in potential energy mgh. I think we can cancel minus and same thing will come. So this is also important, very important. Now 2-3 concepts you need to remember. That if in the question, like if we have work done by external agent 0, or like let me explain you like this. Sometimes they ask, what is the work done by non-conservative force? Achha, non-conservative force, what I gave example, friction. So sometimes in the question now you will see what is the work done by friction. These kind of questions they ask. So work done by non-conservative force, like work done by friction, you can write total energy initial minus total energy final. This is the formula. I am not proving this. Again, we are going for one shot. So you should remember like this. So whenever they ask work done by friction, you can write total energy initial minus total energy final. So what is the total energy? Total energy is nothing but sum of kinetic energy plus potential energy. This is total energy. So this is also very important. Sometimes they ask what is the work done by friction. Okay. Then we have conservation of mechanical energy. What is this? It states that if work done by external agent is 0, if there is no friction or work done by non-conservative force, whenever I say non-conservative force, so first you think about friction only. So if there is no friction, there will be no work done, or you can say work done by non-conservative force is also 0. Then what we can write? Total energy is always constant. Total energy is conserved. Conservation of mechanical energy means total energy initial equals to total energy final. And I have already told what is total energy? Kinetic energy plus potential energy. Means kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final. I'll discuss one question regarding this. For example, this is a ground level and we are releasing the ball from here. Correct? Its mass is 2 kg. Mass of the ball is 2 kg. This height is 10 units, 10 meter. The question is, when the ball drops by 3 meter, see this total distance is 10 meter. When the ball drops by 3 meter, means when the ball is here. Okay, this distance is how much? 3 meter. So at this point, what is the speed of the ball? What is the speed of the? They can ask like this. So see what I am saying, since there is no external force, since there is no friction, there is no non-conservative force, there is no friction. Whenever in the question you see now there is no friction, you can apply conservation of mechanical energy, means total energy through all the points will be same. Means what I am saying, whatever total energy this ball was having at this point, same total energy will the ball will have. Means total energy at point A equals to total energy at point B. I am writing here total energy at point A equals to total energy at point B. Now total energy at point A. I have released the ball. Release means its speed is 0. So kinetic energy is 0. Potential energy of the ball at A. So potential energy mgh. M is 2, G value is 10, H value is 10. Because this ball is at a height of 10 meter from the ground. This is the total energy at point A. Equals to total energy at point B. So kinetic energy will be half. Mass of the ball is 2 V square. Speed at that point. Plus potential energy at that point. Now see here, this is very important. Some students get trapped over here. Potential energy they will write mgh height 3. Height we always consider from the reference level. Like this is our reference level. The initial height also we take. That ball was here. How much height? 10 meter. But when the ball is here, how much height from the ground? This is 10, this is 3. So height from the ground is 7. So you write mgh, m is 2, g value is 10, h value is 7, not 3. So you can solve this equation and you get the value of the speed or velocity. Okay. So by this method you are going to solve this kinetic. They can ask anything: kinetic energy at this point, potential energy at this point, what is the speed at that point. Correct. So this is also very, very important. Correct. Okay. Hope you are understanding things. See, like I'm not saying that entire like chapter will be covered, all the questions will solve, but sometimes we miss the concepts, we forget the concepts. If you see these lectures, like you can see in 1.5x or 2x speed, okay, and it will be highly beneficial for you to revise the concepts. Okay. See, next, see, we will study little bit about types of equilibrium. Equilibrium. Okay. And we'll be talking about conservative force. Like suppose we have conservative force. Whatever I will be teaching right now is valid for conservative force only. So conservative force. So what I told just now, work done by conservative force equals to negative change in potential energy. Okay. So work done by conservative force. Acha, work done. Can I write force into displacement form? Can I write like this? Conservative force dot displacement dr, where dr is the displacement. And just focused on this value. So this is the work done, force A dot like F dot displacement. So dr means displacement equals to, I am writing minus du, change in negative of change in potential energy. So work done, normal formula, force F dot ds. This is F dot ds. So can I write from here Fc equals to minus du divided by dr. See, this dr is going this side, this dr is going this side. So Fc equals to minus du by dr. So this formula also you should remember. Fc equals to minus du by dr. Now, see, if there is equilibrium, what we say, that net force on the particle is zero. So equilibrium, this Fc should be zero. We are considering only conservative forces are there. We have considered, I told, there will be conservative force only. Okay, we are talking about conservative force only. So equilibrium means net force should be zero. Means this conservative force value should be zero. So conservative force is zero means minus du by dr. This is conservative force. Fc equals to minus du by dr. This has to be zero. Means we can remove the minus sign. So du by dr has to be zero. So for any type of equilibrium, any kind of equilibrium, this condition needs to be satisfied. That du by dr value has to be zero. Now listen carefully. We have majorly three kinds of equilibrium. One is stable equilibrium, one is unstable equilibrium, and one is neutral equilibrium. Correct. I will give you examples. Like, see, see, what is stable equilibrium, unstable equilibrium, neutral equilibrium? Suppose there is a ball like this, and this ball is kept in the ball. BALL, ball is kept in BOWL, bowl. Right? Here also similarly here, all these three cases. Now we can see that mg is downward, normal is up, this ball is at rest. Similarly, mg down, normal up, this ball is also at rest. Mg down, normal up, this ball is at rest. Means in all these cases, net force is what? Zero. So net force is zero means they are in equilibrium, first of all. Now if we disturb this ball, first case, focus, if we disturb this ball, it will go to some height, then it will come return back. So if on displacing, the object returns back, this is called stable equilibrium. If it returns back on displacing, so this will be a case of stable equilibrium. Here, if you displace this ball what will happen? It will go down. It will not return back. It will move far away. So if it does not return back and it goes far away, this is the case of unstable equilibrium. Neutral equilibrium, if we displace, neither, okay, it will be displaced to some extent. No, it will not go further. It will not even come back. So this is a case of neutral equilibrium. So always remember, in stable equilibrium, it will return back to its position. In unstable equilibrium, little bit you displace and it will never come back. Means it will continue to move where you have displaced. Suppose you have displaced in this direction, it will get displaced. It will continue to move like that. But here, if you displace little bit, it will be displaced, but neither it will come back, nor it will continue going there. So this is neutral equilibrium. Here what you can see, if I talk about the energy, that is potential energy. So here you can see the potential energy is minimum. So here always remember, in case of potential energy, stable equilibrium, potential energy is minimum. See, it is at the bottom, potential energy is. In case of unstable equilibrium, potential energy is maximum. It is at the top, potential energy is maximum. Okay. So you can remember like this. See, when we go for a party, wedding party, and we are dancing and all, okay, we are highly energetic. So remember like this. When we are highly energetic, we are dancing like this and this and this. Okay. So we are full energetic, means we are unstable, we are dancing like this. Okay. So we are unstable. Unstable means high energy. So unstable means energy will be maximum. Then what happens? After 1 hour you have danced. Now you are exhausted. Now you will take one chair. Now energy is minimum, energy is down. You will sit on the chair. You will become stable. Stable means minimum energy. You can remember like this. Stable means minimum energy. Now mathematically what we tell? See. So first of all, du by dr has to be 0 for any kind of equilibrium. All the 3 types of equilibrium. Now remember these points. If again you differentiate, if d2u by dr square is greater than 0, this is a case of minimum energy. This is a case of u minimum or stable equilibrium. This point you remember. Similarly, if d2u by dr square is less than 0, then it is a case of maximum energy or unstable equilibrium. And if d2u by dr square is equals to 0, so this is a case of neutral equilibrium. Here energy, neither it will be maximum, neither it will be minimum. Neutral equilibrium. One example I will take so that given as x cubed by 3 plus x square by 2 minus 6x. Okay, r or x, whatever. Then they are saying at what positions we are getting stable equilibrium and unstable equilibrium. At what position you will get stable equilibrium and at what position you will get unstable equilibrium. So the first point will be like whether it is stable or it is unstable. First thing is clear now that du by dx has to be 0 for any kind of equilibrium. So first condition is that du by dx has to be 0. So differentiate. X cube differentiation 3x square by 3. X square differentiation 2x by 2. Minus 6x differentiation minus 6. And this du by dx has to be 0. So this 3 gone, 2 gone. So what we are getting, x square plus x minus 6 equals to 0. So you can find that x square plus 3x minus 2x minus 6 equals to 0. So you can take x plus 3 minus 2 x plus 3 equals to 0. From here what you are getting, x minus 2 x plus 3 equals to 0. So from here what values of x you will get? You will get x equals to 2 and another x equals to minus 3. These 2 points you are getting. Means these 2 points are the points of equilibrium. Means at these position, the object, the ball or whatever will be at equilibrium. But they are asking, you have to tell which position point will be at stable equilibrium and at which position point will be at unstable equilibrium. We have got 2 points. You have to find which is the point of stable equilibrium and which is the point of unstable equilibrium. So what we are going to do, we are going to again differentiate. See, du by dx, we calculated it x square plus x minus 6. Du by dx, we differentiated now, and it was x square plus x minus 6. See, I am writing du by dx, x square plus x minus 6. Correct? Again you differentiate, double differentiation, d2u by dx square. So x square will be 2x, x differentiation will be 1, minus 6 differentiation will be 0. Now check whether it is coming positive or negative. We got 2 points. Which points we got? X equals to 2 and x equals to minus 3. We got 2 points. X equals to 2. So let's put. So x equals to 2 you put. So we are getting, see, if you put 2x plus 1 and if you are putting the value, so x equals to 2, 2 to 4 plus 1, 5 you are getting. So this number is positive. Your d2u by dx square value is coming positive, 5 greater than 0. If it is coming greater than 0, it is a point of stable equilibrium, that is minimum energy. Means x equals to 2 is a point of minimum energy. So here at this location you will get stable equilibrium. Stable equilibrium. Now d2u by dx square, d2u by dx square, you check the value for other. We got 2 points now, x equals to 2 and x equals to minus 3. You check for minus 3. So we have got this value. If you check for minus 3, so 2 into minus 3 plus 1. So 2 into minus 3, that is minus 6 plus 1, that is minus 5, which is less than 0. And if it is less than 0, it is a point of unstable equilibrium, or it is a point of maximum energy. Means x equals to minus 3. This is a point of U max or unstable equilibrium. See, again I am saying, if d2u by dx square is coming greater than 0, that will be a point of stable. If d2u by dx square is greater than 0, it is a point of stable. So x equals to 2 is a point of stable. But if it is coming less than 0, means negative, like here, it will be a point of unstable equilibrium. Correct? It will be a point of unstable equilibrium. Okay. So we have covered this definition of force, work energy theorem, kinetic energy, potential energy, spring potential energy, then those relations that work done by conservative force equals to negative change in potential energy, work done by external force equals to change in potential energy. We have seen that stable equilibrium and this unstable equilibrium. Okay. Next, we have two things. One is power and one is vertical circular motion. So, like, okay, let's try, like, we will continue here. Okay, power and vertical circular motion. See, vertical circular motion, or what I am going to do, I am going to take vertical circular motion and power in another one shot I will take. So it will be a less, like, time will be less, some 30-40 minute session. So there I will discuss power and there I will discuss this vertical circular motion. And some constrained motion also I will discuss. So in 30-40 minutes I am going to, like, wrap this chapter. Okay, so like right now, I think I have done with 1 hour 20 minutes. I don't want this video to be too much long. So stay tuned, revise all these concepts. Next 30-40 minutes, we are going to, in the next part, we are going to complete this entire chapter. Okay, so thanks for watching and keep on studying. Thanks. Thanks.